sodium dodecyl sulfate polyacrylamide gel electrophoresis, or SDS-PAGE for short. This video on SDS-PAGE is going to be cut into 4 sections. First, what is SDS-PAGE? 2, sample preparation. 3, discontinuous gel system. And finally, the separation principle. So firstly, what is SDS-PAGE? Well, SDS-PAGE is a common technique that is used to separate the proteins based on their molecular weight. The gel used in SDS-PAGE is called polyacrylamide gel, which is used as a transport medium for the proteins to move through. It is a polymer that does not react chemically with the proteins. The polyacrylamide gel is separated into 2 layers, the first being the stacking gel, which contains a low concentration of polyacrylamide, and the second being the separation gel, which contains a high concentration of polyacrylamide. The stacking gel is at a pH of 6.8, and the separation gel is at a pH of 8.8. This will become relevant later on in the explanation. The stacking gel contains the wells, where we put the protein samples into. At the end, an electrical field is added to the gel, starting negative at the top and positive at the bottom. When the electrical field is applied, the proteins move from the negative to the positive electrode. As they move through the separating gel, they are separated by weight. This is a good general overview of how SDS-PAGE works, but to understand it in more detail, we need to talk about the sample preparation. So number 2, sample preparation. During the sample preparation, we pipette the denaturing buffer as well as the proteins together into a small PCR tube. The denaturing buffer consists of tri-HCl at a pH of 6.8. This will become evident later. SDS, beta-mesaptoethanol, bromophenol blue, glycerol, and distilled water. 2 of the most important right now is SDS and beta-mesaptoethanol, so we'll talk about them in more detail. So SDS, when SDS is dissolved, it gives a net negative charge. The SDS denatures proteins and at the same time binds them in a ratio of about 1 SDS molecule for every 2 amino acids, resulting in the protein or polypeptide chain becoming negatively charged. The beta-mesaptoethanol is important because it is used to cleave the disulfide bonds in the polypeptide chain or the protein. And without it, the protein would not unfold correctly and wouldn't be able to move through the gel based on its molecular weight. So the other important things contained within the sample or the denaturing buffer is tri-HCl at a pH of 6.8, and this acts as a buffer that donates chloride ions. The chloride ions are important and will be explained later. It also contains, the denaturing buffer also contains bromophenol blue, which is a staining dye used to stain the sample blue so that we can see it in the gel. The denaturing buffer also contains glycerol and distilled water, and the glycerol is just to increase the viscosity of the sample, and the distilled water is to increase the overall volume of the sample. 3. The discontinuous gel system. The discontinuous gel system contains something called a migration buffer, which is made of triglycine at a pH of 8.3. And before we start talking about the discontinuous gel system, it's important to understand what role glycine plays. So glycine is known as it is the simplest amino acid because of the side chain, which is just a hydrogen atom. Glycine is known as a zwitterion, which means that in acidic pHs of below 2.3, it is positively charged, and in alkaline or basic pHs of over 9.6, it is negatively charged. In between those two values of around 5.95, glycine is perfectly neutrally charged, which we also refer to as the isometric point. That is calculated by taking 9.6 plus 2.3 and then dividing by 2. Above 5.95, glycine becomes gradually more negatively charged and vice versa. So in the migration buffer of pH 8.3, glycine is negatively charged. When the glycine enters the stacking gel of a pH of 6.8, the negativity of it decreases and so does its mobility. In the stacking gel of a pH 6.8, we have chloride ions, protein SDS complex, and glycine. All of these are negatively charged. They migrate in this order. The proteins are stacked between the chloride ions and the glycine, and that's why it's called the stacking gel. In the separating gel of pH 8.8, the migration takes place in this order. The glycine is much more negatively charged in a pH of 8.8, and that's why it travels faster than the proteins. Then lastly, we have the proteins. Now finally, why do we have two different gels? The problem is if the sample went straight into the separating gel, then the proteins would not all go in at the same time. However, with the stacking gel, the proteins all stack together due to the low pH and low mobility, and then all together they enter the separating gel at the same time. It is also important to mention that none of the proteins get stuck in the stacking gel due to the low concentration of polyacrylamide gel.